Hi and welcome to Object-Oriented Programming 1. Today's topic is polymorphism, exceptions, and also, the last part will be about casts, but the main topic today will be polymorphism and exceptions. And when we now have a look at the lecture schedule, we can see we are already halfway done with the lecture. So we are heading now into the second half of the lecture. There is going to be just one more lecture before the Easter break, and then 2 more lectures after the Easter break, concluding with operator overloading and templates.
Yeah, and next week there is a double stint of the practicals.
Yeah.
So we have free and you do all the work next week.
Okay, before we start with polymorphism, let's do a recap of last week's lecture when we talked about inheritance. For this, we have prepared a short quiz here.
It's not that short.
Yeah.
Again, we have constructors, we have base classes, derived classes. I think in the practicals you will see all this inheritance next week, but we already talked about that last week. And again, we have the same animal class.
Mm-hmm. Yeah, we just forgot to mention, please join again on Slido, either using the QR code or visiting slido.com and entering the code displayed here. And you should be able to see a few options of which you can select the answer.
This might take a few minutes, so we will give you a bit of time, of course.
We didn't have a shark and a bee last week, right?
No, last week we had, what was it, a lion?
Lion, yeah.
And
we had Simba.
a fish, I think.
Yeah.
Yeah.
To make the sound bloop. Yeah, and here in the main function, we are creating 2 objects, a shark and a bee. And then we delete them immediately.
Okay, so what do we want to know here? I think firsthand the ordering. So what is called first, base class, derived class. Then the same when objects are destroyed. So this is what we extensively talked about last time. Let's wait, maybe if we can reach 40.
Mm-hmm. Sure. So in which order are the constructors called? In which order are the destructors called? And which destructor and constructors are called?
I'm not confident that we can reach the 40, so maybe
let's continue.
Let's see what you voted for.
Should we wait? 37? No.
Oh, let's continue. Okay.
And
okay, so
yes.
Maybe we did something wrong last time. Let's walk through that step by step what happens here.
So we create 2 objects in the main function. First, we create a shark, which is of type shark. So we have here this variable shark here. It's a shark pointer. And the object type is shark. Okay, this means it should be, first animal, which is called. So the constructor of animal is called before the constructor of shark is called. So we now have the first 2 characters, which is A and S. Then in the next line, we create a B object. But here the B object is, or the B variable name here is of data type animal pointer. Yeah.
There is the aha moment. Yeah.
And
So the B is created.
B is created, and again, first the animal constructor is called, and in this case also the B constructor is called. So all good so far. But now when we delete the shark, okay, we have created a shark here of type shark pointer, and the object type is also a shark. When we now delete the shark, we will first go into the destructor of shark and then go into the destructor of animal. So it's the reverse order. Okay, so far so good.
Yeah, but we only have one A left.
We have one A left and no more B. So in this last line of the main function, when we now delete the B, it's of object type B, but the data type of the variable is an animal pointer. That's why only the destructor of animal is called, but not the destructor of B. And that's the reason why we have SAA for the destructors and not SABA.
Do you have any ideas how we could solve it so that also the B destructor is called? Yes. Yeah, what do we have to write there? Virtual, yes.
Exactly. So the solution would be to add the virtual keyword here for the animal destructor, and if we add this keyword, then also the B destructor would be called.
Yeah.
But since we don't have a virtual keyword, only the animal destructor is called.
If you have a configuration or program like this, you will have a memory leak because the B part of the animal is not destructed or destroyed, only the animal part. So in this case, you have to write virtual in the destructor. And yeah, I would say in most of the cases when you program, just write virtual in front of the destructor. It saves you a lot of time debugging errors like this if you have memory errors.
Yeah. So the memory leak could appear here because this code here is never executed if the destructor of the base class is not virtual.
Any questions to this? This is maybe one slide summary of what we did last time.
Yeah.
So if there is no question, I would have a question to you.
Yes.
Can we create animals in real life that are not of a specific type?
Not really, right? So there's no thing such as an animal which we can pet, for example, or which can eat. It's not a concrete thing in real life that we could create.
Animal is just like an idea of a group of different types, a lion, a bear, a fish, whatever, but there is no animal, it's just an animal. So we somehow want to prevent to create an animal. How can we do that?
We can do that in C++. It's a very cool feature. We can do that with abstract classes using pure virtual methods. If we think about abstract classes, so for example, we have animal. Animal is more like a general concept for all the specific animal that have a specific type, but an animal itself cannot really exist. So we just want to define some behavior that all the animals share, but the concrete implementations depend on the specific animal that we want to create. For instance, a lion, shark, whatever. And what we have to do when we want to define a class as an abstract class, we have to set at least one method to 0. So this is the pure specifier. And if this method is set to 0 and it is virtual, this means that the class is abstract, which means we cannot create an object of this type anymore. And for example, for animals, we don't want to create animals or objects of type animal. But when we have an abstract class and we have one derived class or many derived classes, we must implement all the methods, all the virtual methods, which are set to 0. Otherwise, we wouldn't know what is the concrete behavior, the concrete implementation of this specific method in the derived class or classes. So whenever we have a virtual method that is set to 0, so a pure virtual method in the base class, we have to implement them in all the subclasses. Yeah, in C++, we sometimes call the abstract classes interfaces. In Java, for instance, there is a differentiation between abstract classes and interfaces. They have some, kind of different behavior, different properties, but in general, it's enough to say in this course that abstract classes are kind of interfaces. And all these abstract classes, these interfaces, have to have at least one virtual method that is set to 0. And when this condition is true, then we cannot create an object of this class. So we cannot create, for instance, an object of type animal. And as said before, all the subclasses that are derived from the base class, of the abstract base class, they have to implement all the pure virtual methods. So all methods that are set to 0 and that have the virtual keyword. And why do we even use that? I think we have discussed enough about this. For instance, all animals can, I hope, move and also eat.
Not quite sure about move, but yeah.
To some extent. But yeah, of course, they do it differently. So fishes move differently than lions, for example. Are there any questions to abstract classes before we go more into the definition of polymorphism?
Seems to be an easy topic. So
Hopefully.
it is really just setting one function, one method to 0, and then you cannot create an object of it. That's basically it.
And implementing these functions then, or these methods in the subclasses. Okay, if we now read through these sentences, polymorphism means that an object can have many forms. Runtime polymorphism can be achieved through inheritance and virtual functions. Yeah, what does this mean? We can have a base class, we can have subclasses. So we can have methods in the base class that are implemented in the subclasses, which do different things. So for example, animals move differently. And through inheritance and these virtual methods, we can at runtime, so after compiling the program, at runtime decide which method or function is then called actually. This is what polymorphism means, that it can have many forms. And more concrete or more programming related, when a function call is made through a pointer or reference to the base class, so to a virtual function of the base class, then the appropriate derived class function is called at runtime based on the actual type of the object being referred to. So this is just a more formal explanation of what we have seen before. If we have, for example, a lion, and we created this lion, it has the type lion. So the object has the type lion. If we have, let's say, a fish, we create an object of type fish, and both of these objects then call the function move or eat or anything else. They will have a different behavior based on the object type. So if there is a different implementation for these methods, depending on the object type, then the different behavior is also associated with this. This is actually what polymorphism is. It's a complicated term, but in fact, it's not that complicated. Any questions to polymorphism so far?
So it's basically just the term
Yep.
we applied in the last time, and now every time when we write virtual polymorphism is like the term how we call this.
Yeah, true. We have also, kind of diagram here, which describes polymorphism, because we now have a different behavior depending on the compile time and the runtime. For compile time, polymorphism, we have function overloading. We have talked about it, I think, in the first lecture.
The first one, yeah.
Which means we can have different functions or multiple functions with the same name, but they have to have different number of parameters, different order of parameters, or the parameters have to have a different data type. But we can match them by their signature, so name plus the parameters.
So the compiler always knows which function to select.
Yes, we know this at compile time.
Yeah.
The same for operator overloading. We'll not go into detail here because there's one dedicated lecture for this. But this is also recognized at compile time, which operator or function is then called. And in comparison to that, we also have runtime polymorphism. And this is exactly what we have seen just before. It's overriding functions, so defining a function as virtual in a base class, and then having a different implementation in all the subclasses, or in just a few subclasses. And this is then decided during runtime which concrete method is called. So we don't know it during compile time, but we know it during runtime.
So the question here now is, how does we determine which function to use at runtime?
That's a very good question. And when we talk about polymorphism, we often talk about virtual tables, or short, vtables. And when we now have this example, this code snippet here, very basic one, we have a base class which has a virtual method speak and a non-virtual method sing. We also have a derived class, derived from the base class, and there we have a method speak, which overrides the speak method of the base class. Okay, there's nothing new so far. We create here a base object and call the speak and sing method. Okay, we already know that.
So we create a derived object but store it in a base pointer.
Yeah, thank you for that. Yeah, exactly.
So what we want to have here like this, when we call bSpeak, we want to have, because it's a derived object, call this function. When we call bSing, we want to use this function here because it's not overwritten in the derived class. We just want to have it from the base class.
Yeah, that's the desired behavior we want to have.
How does this work now? So it's virtual, and it will work like that because this one here is virtual. And as soon as this is virtual, we will have, even when we store it into the base pointer and call bSpeak, this one here gets selected and used because in the base class it's virtual. Yeah.
We will now dig a bit deeper, not too deep, but a bit, and we will have a look at the virtual table. We can all create or have a look at the virtual table of all the classes, or let's say of actually everything regarding this program here with this command, so you can also do it. And this creates a dump of all the virtual tables here, not only virtual tables, but this is also included. And we can now see that we have multiple entries for the base class, so the vtable for base. There we have some stuff. And here we have the speak function, or the speak method. And in the base class, we also have the sing method. And then when we have a look at the virtual table for the derived class, we see, okay, we have a base sing here, it's not declared as virtual in the base class. But now probably the most interesting part here in the virtual label for the derived class is this line, which is derived :speak. And this means there is, or in the derived class, there is a method that overrides the speak method from the base class, and that's the reason why we have the derived speak in the virtual label for the derived class. We don't have it for the sing method, so whenever sing is called for any derived object, then the sing method of the base class is called. But when we have a derived object and the speak method is called, then we use the speak method of the derived class.
So again, this vtable might be a bit hard to understand. As soon as you write one virtual keyword, in this case into the base class, we last time said that you have a bit of overhead because you have to store more information. As soon as you create one virtual method, this vtable is created in the background for this class. And this vtable then defines where the functions are stored. So these are basically just pointers to functions. Where is the speak method of the base class? And in the background, this is just a location, just a memory location. Where is the function of the sing method? And the same for the derived class. As soon as I have a virtual in the base class and I override it in the derived class, the table is created in the background. So I have a bit more memory consumption because I need to store this table. But yeah, I think in 99% of the cases, it's fine because it's not that extensive. And in this vtable for the derived class is now listed, and we can use the sing method from the base class. But if there is an object that is from the derived class, please then use the speak method from the derived class. This is all the magic behind this virtual keyword and these vtables. So during runtime, the program then have a look into this vtable and sees, okay, which speak function do I have to use? Should I use it from the base class or the derived class? No, I can use it from the derived class because I have a derived object and this is the correct function to use. That's all.
Yeah, as you said, it's because of the runtime decision. So we decided runtime, okay, is the, let's say, speak method of the base class called or the speak method of the derived class. That's why we need the virtual labels.
Any questions to this? This is, of course, a bit of background knowledge, not really necessary to know when you're programming, but it might explain a bit the concept. Yes?
This here.
Why are all these pointers integer pointers? There
is a specific reason.
Did you create the example? I cannot remember, to be honest.
Yeah.
It doesn't matter, to be honest, because pointers are always pointers. I don't know if there has a specific reason to be an integer pointer, but pointers are pointers. They're
pointers.
all 8 bytes, so it doesn't really matter. Yeah. But good question. Never thought about that.
No.
Any other questions? If not, then we could move on to a highly discussed topic today. And Michi and Julia always say we will discuss that later in the lecture. Now is the time for a very well-known problem. And I think also you also had most of the time in ESB.
Well-known and also a bit annoying, I would say.
Yeah. It produces a lot of code.
Yeah. So when we write this code here, we have a function called getConfig, and we check if the content is a null pointer. So we want to open a config file, read from the file, and we check here if the content is a null pointer. We have done that in ESP. So nothing special here. Let's have a look at the getConfig function. GetConfig function, okay, this will call another function called readFile. And again, if the config that is returned by the function that we call here is a null pointer, we return a null pointer back to the main function. Okay, yeah, it's just one function. But now we want to call another function here in the readFile function. It's the openFile function. We pass the file name in the file. And again, if the value returned from this function here is null, we return a null pointer. And yeah, this is then catched here. Oh, I'm using catched or caught. I shouldn't use this. And here again, yeah, the null check is done, and then we print the error message. So we have another function, it's called openFile. There we actually want to open the file, and then we see, okay, we cannot open the file, doesn't exist, or whatever reason, and this returns false here. So we have the function called getConfig, which calls then readFile, which calls openFile. And we always have to check here in the readFile if the returned value is false, then we return a null pointer. And here we again have to check if the returned value is a null pointer. And in the main function, we again have to check that there is a null pointer. And after that, we can then say, okay, there is an error in opening the file.
I hated that because when you are deep nested into functions, you have to propagate the error to the main function, and then you can react. So for example, if the file cannot be opened, your program should end. But yeah, there's a lot of code writing, always checking return values, and it's very, very annoying. So basically, on the next slide, what we are doing, we have a main function that enters the getConfig function, that enters the readFile function, that enters the openFile function. Here is the error. Okay, let's go back to the readFile function. Let's go back to the getConfig function. Let's go back to the main function.
Yeah, annoying, as I said. So we always have to propagate the errors through all the functions that we call, all are propagated back to the, in this case, the main function. And each function must handle the error. So we always have to check, is there an error? Okay, then we return the error until we are back in the main function. We always have to propagate the error through all the functions that we call. I would say for 3 functions, yeah, it's okay. But if there are more functions or other functions that then call some of these functions, it's really annoying.
The cool thing is there is a solution in C++.
Finally, we have the exceptions.
Finally, we are talking about the exceptions. So exceptions will help us a lot.
Yeah. How does it look like when we want to use exceptions? Yeah, it's basically just throwing exceptions. Like throwing a water balloon, we can throw away this exception and someone else should handle it, should catch it. We'll come to that soon. But if we only throw it, yeah, probably no one will catch it, so there is no action here. The error is just thrown away, but somewhere or someone should catch the error. And for this, we can now use this try catch block here. So we have this try block which calls, or with statement that calls the getConfig function, and wherever now error occurs, we can now catch this with this catch block here, and then say, okay, we had an error in opening the file. And the good thing here is that the getConfig function and the readFile function doesn't have to care anymore. So they can ignore that they should return some error message, some error value, they can just call the, in this case, read file function, and in this case, the open file function. And yeah, whenever an error occurs here in the open file function, we just throw the null pointer, this case, and then we catch it in the main function here. So reduced code in these two functions, and a try block and a catch block in the, in this case, main function.
This try catch might look a bit odd in the beginning, but try just means try to execute it without throwing an error. If it works, it's fine. But if there is an error inside this try block and all the functions inside, then I will catch the error. So basically you can throw something and nobody is catching it, or you can throw something and somebody is catching it.
Are there any questions so far regarding exceptions? Yes?
We're here throwing an exception in a void function, so a function that doesn't have to return anything. But in case we are throwing an exception, we have to return a value, so how do we do that?
Very good question. So in this case, we have the void function here, open file. And what you meant is that we somehow return something, although it's a void function, right? This is the case because we don't really return something. So these two functions know nothing about the fact that here an error is thrown, an exception is thrown. It's not really a return statement. It's more like, okay, here is an error, we throw an error, and now we go back to the code section where this error is maybe caught. We don't know. In this case, it is caught. But if we wouldn't have a try catch block, we will see what happens in a few slides. But it's not a return statement. It's more like the information, okay, go back to where it was called and check there if there is someone who will catch it.
So we will discuss that in the next slide. And if there is still the question is open, then we can discuss that, yeah. It's because the basic principle, what you meant, it makes totally sense, but these exceptions are kind of higher ranked than all the other instructions. So these exceptions mean they can stop the execution at any point in the program. So all the code segments, whatever you write the code afterwards, they are not executed. It stops the execution at this point where the exception is thrown, and it then continues completely elsewhere where you catch this exception, or if you don't catch the exception, then the program ends at this point. This is the basic principle. So you don't really need a return statement, or it doesn't have to match with the return statement, because it does not influence the return statement at all. The throw is, again, another way to propagate information out of the function, besides the return value. Does that clear it a bit?
Yes, but I think when you asked me if I misunderstood you, my question was when we have a non-void function that is supposed to return a value, and we encounter, we throw an exception in it. Do we have to first return some value that indicates that an exception is encountered, and then throw the exception? How is that?
So your question is when we have a non-void function. So maybe we would throw in the read file, for example, where we return a char pointer. Do we have to return the char pointer first and then throw? That was your question. Okay. No, you don't. You don't have to. So you can completely kind of ignore the return type just throwing this exception means you cannot handle the return value anymore, because this is so much higher in the hierarchy, and a usual or this function will not end as usual with a return statement, but at this line where this throw happens and there is no return statement. And it would only continue when you catch this exception. But let's move on maybe to the next page, because we have a more detailed description of different parts.
Yeah. So again, we have, let's say, 3 parts here. We have this try block here, which means that all the statements, all the code, all the functions that are called, so we can have multiple nested function calls here, all of this is checked if an exception is thrown, and only if this is inside of the try block here. Yeah, we can then somewhere throw an error, or someone else throws an error, and this means that an exception occurred. So the throw keyword means whenever throw and something else, in this case error 1, or as we said, saw it before, the null pointer is thrown. This means, okay, an exception is thrown, an exception occurred, and we should somewhere catch it, else the program ends. But we'll see that soon. So we have the try block and we have the throw keyword here. And then we have one catch block. We can have multiple catch blocks. All of these catch blocks do some kind of error handling. It's an error handling section. We can have different exceptions. We'll see that soon. And yeah, handle the different exceptions differently. We can do something depending on the type of the exception. But yeah, it's important that we catch the exceptions. And yeah, we can then react depending on the type of the exception differently. So these are the 3 main parts of the of exceptions. Okay.
Let's have a look if you heard what I said before. What is the output from this code snippet?
So we can see it here. We have this try block. We have a throw keyword here in this statement. And we have, in this case, just one catch block. So what is going to be the output of this code snippet?
Ah, thank you.
I caught it.
Maybe we have to throw something again later. I love exceptions because it's the first time that we don't have this line-by-line approach, and we move around, and this can be very complicated in the beginning, especially when throwing something and catching it then completely on another line in the program. Okay, last few seconds, please decide.
35 again. Yeah. Okay, let us see.
Yeah.
Awesome. So, most of you got it correct. Let's have a look at the example here. So we have this try block here. We print here cat. Then we throw an exception, or throw 4 in this case, and then we print tog. And we have this catch block here, which prints exception whenever an exception is thrown in this try block. And yeah, as you said, all the code that would be executed after the throw statement here is ignored, omitted. It isn't executed. And yeah, thank you. And we directly jump into the catch block, and all the code in the catch block is then executed. So dog is not printed, but cat is printed since it's before the throw statement here. And then we directly jump into the catch block, and then exception is called. And then all the other code.
And this can also be, of course, if there are 2 or 3 sub-functions that are in this try block, and any of these functions will throw at some point an exception. And then we can, so it stops immediately there, and it continues here in the catch block. What's also important, I think we didn't mention that until now, is whatever you are throwing here. So this, in this case, it's an error code. Maybe 4 stands for something important. Whatever you are throwing here, you have to catch the data type, and then you will come into the section. If you throw here a 4, but you will catch, for example, a double or a pointer or whatever, this will not work.
Yeah. So the data types of what you throw and the parameter here in the catch block these have to match.
Yeah.
So if you throw something that is an int, you have to have a parameter of type int here.
What kind of exceptions can we throw?
Yeah, C++ is a cool language. It's an object-oriented language, and we now have some classes that we can use for exceptions, or that are already implemented that we can use. And there are some standard exception classes. Again, very cool. We have this inheritance here. So we have one base class. It's called SED exception. And then we have a lot of derived classes or derived exceptions based on the exception class. We can all use them. We can just catch them whenever we want. And maybe we can have a look at a few of them. Yep. So, for instance, when we use a vector, in this case of type int, and we want to access the 5th element, so at position 5, but we only have 3 elements, this does not work. In C, we would have a beautiful segmentation fault.
Yeah.
But C++ is a bit more helpful. It throws an STD out of range exception. So this is one specific class here in this hierarchy. And it's derived from the logic failure or logic error, I think it's called. But here we can just assume whenever we want to access an element that is not within the range of the elements that we could access in a vector, then somewhere a standard out of range exception will be thrown, and we should catch it.
I have a question to you now. You said before that in C, the segmentation fault occurred as soon as we accessed the vector at position 5, or not a vector, an array at position 5, and there is no element at this position. And then you said, with the vector, it throws an out-of-range exception, and it's better. Any ideas why it's better to throw an exception instead of having a segmentation fault? Yes?
Because we can catch it?
Because we can catch it, yeah. The segmentation fault means your program is over. It's done, yeah. And maybe this segmentation fault or this access is based on a user input, and he wants to access this fifth element, and you did not program it right, so you haven't checked the borders, and then this is, it terminates your program with this kind of implementation. So let's say the user inputs, I want to access number 5, and it only has 3 elements. This vector will throw this out of range exception, but then you can react on this. Then you can say, okay, if the user is so stupid and he wants to access this fifth element, let me just catch it, and then I can react. Maybe I can print out, it's out of range, don't do this. Then we can start once again with the user input. So this is a huge advantage compared to the segmentation fault, because you have much more control over your program with less code, because all the vectors and all the functionalities you are using, they are throwing these exceptions. And you can just catch it and then react on that. Another example is the standard string to integer. And we also, again, know it from C. This, I think it returns null at some point. I think it's null, yeah. Can't remember exactly. But in this case, it throws an invalid argument exception, which just means I cannot convert this string to an integer because it's maybe ABC.
But again, we can catch it, so we can react on this behavior that we don't really want. But
the user should input a value. It should be 1 to 5, so a number. But then the user decides to input ABC. You have no control over user input, but you can catch this invalid argument exception, print out, you should enter 1, 2, 3, 4, 5, and then try once again with the user input. Much easier to write code.
Okay, so these are just 2 exceptions. We have the out of range exception, the invalid argument exception, and now the question, what happens if there is no more memory on the heap that we want to use?
Yeah, I think Michi today said we don't have to worry about that.
That's great.
Now we have to worry about that again, but it's not that complicated than it is in C. Not for A1, yeah.
Yeah, that's true. The bad alloc exception. Again, it's derived from the standard exception class. And you must now catch the exception and end the program whenever the bad alloc exception occurs. Usually we do this in the main function. Yeah, it depends on what you're doing, but usually
I think it's the best way.
Yeah.
But again, remember, and when you are down into the functions, you have 3 subfunctions, 5 subfunctions, and then there is no memory, so you have to propagate again, null, 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 back to the main, and then end the program. Again, this is not necessary anymore in C++, because new will throw this bad alloc exception, and you just have to catch it in the main. That's basically it.
Yeah. So whenever we create this pointer here, in this case, with new, so we allocate memory on the heap, we don't have to check, okay, could it be null, what was returned, or can I use it? And the only thing we have to do is we have to write this in the try block. So we call func here, and all the code that is executed here is then in the try block, and any exception that is thrown, or in this case the bad alloc exception, is then called in this catch block here. So we only have to care about this, or most of the time, in just one place in the code, and not propagate it through all the functions anymore. Yeah, and then we free some other memory if we have some, and either continue with program execution or end. This is basically, handling memory or no more memory in C++.
Yeah, but until now, we always caught our throw. So there was always a catch block that took our throw and then worked with it. What happens if there is no such section? So let's say we have this vector.
And yeah, we want to access now the 10th element. But yeah, as we can see, we have 3 elements in the vector, so there is no 10th element. Yeah, this will throw an out of range exception as we've seen before. And that's the reason why, or it is thrown and not caught, and that's the reason why the program terminates. So whenever you execute this code here, you will then see the message, something like terminate, called after throwing an instance of, in this case, std out of range. And then you will see, okay, you want to access the 10th element, but in fact, the size of the vector is only 3.
Yeah.
So yeah,
it's pretty similar to the segmentation fault, but it at least gives you a description what went wrong and which exception was thrown, and maybe you should have caught that.
Yeah, so it's a bit more of information at least, but again, let's say the user inputs, then we don't want the program to crash. So we should somewhere catch the exception here, or all the exceptions, otherwise the program will terminate with an error message as shown here. And for this, we now again have a quiz, a short code snippet. Maybe important for this one is which type of exception is thrown, but I don't want to spoil too much. So we have try block here, a catch block here, and again we create a vector, access an element, then
use this string.
Use this string to int. Okay, looks
convert
weird.
it, yeah.
Yeah, okay. Then print something, and also in this catch block here, we then print something. Does it work to convert red to an integer?
Let's see.
Yeah, let's see.
There is a race between 3 answers, I can see.
Okay, let's reach the 35 again, and then
last seconds for you to decide.
Very curious. Okay, let's have a look at your answers.
Okay, most of you said I.
Why?
No, most of you said runtime error.
Yeah, of course.
Why a runtime error?
Why is it a runtime error? Yeah, as most of you initially at least thought that this would cause an exception. Yes, it throws an exception, but in the line before, there's also an exception that is thrown because we access element at position 2, but we only have 2 elements, so we can only access the elements at position 0 or 1, but not at position 2. And whenever we access or try to access an element that is out of range of the vector, so out of the boundaries, then we will receive an out-of-range exception. And we don't catch this out-of-range exception anywhere because we only catch the invalid argument exception. This would be totally fine if we would access the 0th element or the first element in this line, but since we access the second element or element at position 2, an exception is thrown here. This code is not executed anymore, and we are waiting for someone or for a code section that will catch the out-of-range exception. But we don't have this section in this code. We only have a catch block that can catch an invalid argument exception, but not an out-of-range exception. And that's why this program terminates. It ends with the information here, with this error message. Okay, again, STD out of range. We want to access the element at position 2, and the actual size of the vector is 2, so we cannot access the element at position 2. So we would have to catch this exception also here as an additional catch block.
Any questions to this? Yes.
Can we do an overall exception error catch?
Very good question. Can we do an overall exception catch? So catching basically all the exceptions. Yeah, we can do that, and we'll come to that now. Yes.
Could you once again explain what this line using namespace STD does?
Yeah, of course. So using namespace STD means that we don't have to specify the namespace identifier, which is STD standard, but we can just simply use all the elements, all the functions that are defined in this namespace. So it's a huge namespace, STD standard, and whenever we write using namespace STD, we don't have to write, let's say, STD cout or STD cin. We can just use cout, cin, and all other elements in the namespace.
Or
This example, you use it anyway, specified.
did we use using STD somewhere? Ah,
Oh,
here.
I'm sorry.
Oh,
Yeah.
Ah, okay.
That's true.
That's
Yeah.
true. Doesn't make sense here because we are always using STD,
STD,
yeah. And you should not use using
No,
STD
no.
Namespace. Good point.
Yeah. Thank you. Sorry for that.
We have to remove that line.
So yeah, absolutely doesn't make sense here.
Okay. Until now, we talked about existing exceptions and which are in the standard library, but we can also create our own exceptions. And this is also very cool. But before, we need to know, I think, one or two keywords. One keyword is the so-called no-except. Basically, very, very similar to the const. So if you remember, const means we are assuring that in this case, get age, I will not change my current class. So in this case, maybe increasing the age or whatever. And no except, so this is another specifier here, which you write after the function definition. And this just tells the compiler that this method will not throw an exception. Not only this method, but all the methods that are called inside this function. So there will never be an exception. Sometimes you need that, or at least it's very good practice to write it there, because you can now assure that this will not throw an exception. That's basically no except, just a keyword.
It's like a promise to the compiler or to other programmers that, okay, in this function and all the other functions called here in this function, there will not be an exception thrown.
And now it's getting complicated because we have to have a look at the standard exception class. So the base class of all the exceptions in the standard library, because this one has a method that is virtual const char pointer what const no except. This is the function name. This is basically the return, or the return type is a const char pointer, so it returns a string that you cannot modify. It assures that this function here will not modify the content, and it will not throw an exception. And it's virtual because you can derive from this base class and create your own implementation. And this is what we want to do now. Because when we want to create our own exceptions, we always want to derive from the base class std exception. There is so much functionality already there, so we want to reuse it. But what we have to do is we have to use this what method. So when we create our own OOP1 exception, we can create a class, something like this, create a class OOP1 exception. We want to inherit it from the std exception class. We create maybe a private member because we want to have a specific message to our user. We have this constructor where we can hand over the message, then we set the message in the initialization list, and then we override. This is even more complicated. Virtual const char pointer what, const no except override, but you should be now familiar with all of these terms. And this basically just returns this string here as a C string because this what function returns a char pointer and not an std string. I know it's complicated for now, but this is basically always the same when we create our own function. So this is kind of the template you can use. And now, if this is your program, you can create your own create array function, and now you can throw your own exceptions. And in addition, you can hand over a specific error message here. So you call the constructor, the error message is inside this message, and at some point you can now read whatever you have written in here. So for example, if you have this main function and this calls this create array, this immediately throws your own exception with we crashed our program as our error message. And then we catch it here. So we grab catch OOP1 exception reference because we don't want to have a copy. This is just the variable name of our exception. And then we can call our ewhat method. And this ewhat is basically what we have overwritten here. And this ewhat returns now my error message here. So we crashed our program is basically the output of it. I know there's a lot very complicated stuff in there, but in short, override the std exception class, or derive from the std exception class, override the what function, then you can throw it with your own message. This can, for example, also be telling the user something, and then catch it at some other point and print out whatever you have in there. In this case, it doesn't make much sense because we have only one case where we want to print we crashed our program. But imagine if we have our create array function, there's a lot of different cases. And at one point, we want to say to the user, do this. And at one point, we want to say, that's wrong input from you. So we can specify this in the specific location, what we want to tell the user. And then there is always one catch block that then prints what we defined in the case here. So you do something wrong, do this, whatever. So it again saves a lot of writing because you combine all the messages for the users, for example, to one specific location in this catch block.
And again, the data types of the exception you throw here in the create array function must match the data type of the parameter in the catch block. So let's assume you would write catch const, let's say out of range exception. The OOP1 exception would not be caught here. So it really has to match the type or be derived. Otherwise, this exception is not caught.
Yeah. And now we are coming to the question you had before. Can we do it more generalized? And yes, we can catch more than one exception. So if we have here a do function method, which I don't know, but maybe it throws some kind of exceptions, I can catch many of them. So maybe I want to react on my OOP exception differently than to a bad log exception, which makes sense because maybe this OOP exception is a wrong user input. Bad log exception means I have no more memory, then I want to maybe return my program or end. And in any other cases, this catch block here catches all the other exceptions because this is the base class and it catches all exceptions that are derived from this base class. So this will catch out of range, invalid argument, and all the other exceptions that are derived from this base class. So in general, if you have this STD exception here, your program is very, very unlikely to have to exit in any case, because you will always end up in this catch block for all of the exceptions.
So any exception can be thrown, and in this catch block, any exception will be caught.
Yeah. The important stuff here is the first fitting catch block is used. So if I have in my do something function, it throws an OOP exception, this one will be used. If it throws a bad log exception, this one will be used. And all the others are used or are caught here. Now, one more question for you. What is the output of this one?
So in this code snippet, we assume to have, again, an own custom OOP1 exception that is derived from STD exception. And in this case, we again have two catch blocks. The first one catches STD exception, and the second one catches the OOP1 exception. So what is going to be the output? Okay, maybe we can reach 35 again. Or let's say 30.
Okay.
Last seconds.
Let's see
Then
if you heard what I said before.
heard, probably yes, understood. We will see.
Yeah, it looks good, to be honest. It looks very good.
Awesome. Great.
It's printing general error. Why? So, as I said before, the first fitting exception is used. So I throw an OOP exception and I catch it here, but the OOP exception is derived from my STD standard exception here. And when I kind of compare them and I say, let's say it in words, is the OOP exception an STD exception? We are again into inheritance. It's the same as I said, is the lion an animal? And that's true because it's inherited from the animal. So this block already fits because the OOP exception is a standard exception, and this one will print it, and the other one will not be printed. So you only get always in one catch block. But very, very good.
Yeah.
We have a very nice animation now. Yes.
Yeah.
Could you go 3 slides back for one question?
This one?
Moment. There was this class definition of OOP1.
This one here.
Do we need this virtual keyword in the derived class?
Oh, good question. Yeah. Do we need this virtual keyword in the derived class? Not really, but I would highly recommend to write it, because at some point you may decide that you have one specific case again of an OOP exception, and you are deriving again from the OOP exception in a more specific derived class, and then you would need it. So let's write it there to be safe if you have more plans extending your program. Yeah.
Yeah, so the additional effort to write the virtual keyword in front of the method here is definitely less than the additional effort or potential additional effort for finding the bug.
So basically, as soon as you have one virtual method in the base class, I will always write it in all the derived classes, because then I know I will never have problems when creating new derived classes.
Okay. Any other questions to exceptions? Yes.
Yes.
Why don't we just use the general exception? Why do we use that allocation or something like that?
Good question. Why not use the standard exception? It's up to you in general, but you can add more specific implementation, whatever you want. So in this case, you can add your own string and your own error message. You can maybe also react another way. So maybe you just not only want to print something, you also want to, I don't know, call another function which removes some other vectors or whatever. So there might be cases where you want to have your own exception implementation to do some stuff when this exception occurs.
Does this answer your question? Great. Yes.
Okay, it's maybe a weird question, but the way I see it, you can basically make a function that gives different return types depending on what you throw. Are we technically allowed to do that? Like make a function that gives char or an integer or something else depending on what happens inside of the function. And we catch it accordingly.
That's a very, very good question. So I think what you meant is, are we allowed to throw anything out of a function and then catch it at some point? It somehow is against the return one type of a function. And I think we didn't mention that till now. You should only use exceptions in case there is a problem. So in case there is an error. You should not use exceptions for your normal data flow, your normal program flow. So if you have, okay, everything is fine, then you should not throw an error, because it's some kind of a go-to statement, and we don't like go-tos, because you can jump on a completely different location in your program. So only use exceptions when there is an error. So maybe a user error, user enters something what you don't want, the vector or any other data structure you're using throws an error. Then you can use it. It's very good for example, detecting wrong user input. But if everything is fine, then you should not throw an exception. And we will have a look at that at the assignment interviews, and you will get a point deduction if you throw random numbers because you want to have it somewhere else. This is against what we want to do in structured programming. Yes?
So if we had, for example, a program like assignment 4 in ESP last year, we literally had a command prompt. Can we throw an exception when a user, for example, enters a command with an invalid number of arguments? Is that a valid cause for throwing an exception?
Yes, exactly. So just to repeat it, if you have a command, like a command enter from the user, and the user enters too many or too less parameters to this command, this is a perfect example for an exception, because you only have to count how many spaces are there in between or how many words are there, and if it's not fitting the exact number you want to have for this command, then throw an exception and say, okay, that's invalid, let's start once again. Perfect example for that. Any other questions, comments, or whatever?
In the meantime,
Yeah,
we have prepared this animation. So on the left side here, we call the function 1 in the main function 2 in function 1, function 3 in function 2, and then we see, okay, yeah, in function 3 we throw any exception. What then happens is we go back to now function 2, function 1, and finally in the main function, okay, yeah, there is an exception, there is a bug, we should somehow handle this, we should catch it.
But we don't have to have it in the main always.
No.
We also can have it in another function. So let's say we, again, same function 1, function 2, function 3, then we throw the exception. And then just one step back in the hierarchy, we identified the bug.
We can remove it.
We can remove it and then start again.
And yeah, I think let's conclude with the summary for exceptions. Yeah, exceptions are a great feature that we can use in C++. They are great to throw errors over many functions. So instead of propagating through all the functions to catch the error and return it back to the, let's say, main function, we can just throw it and then catch it somewhere in the code. And we can use the standard exceptions, so exceptions that already exist in the C++ standard. These are just classes and derived classes, or we can create own exceptions, in the best case derived from an exception class. It is a concept that is used in many programming languages. If you write code in Python, in Java, in C#, or many other languages, there is the same concept, similar concepts with try catch blocks. So throw an exception somewhere, catch it somewhere. And yeah, as you said, use exceptions only for errors, so don't use them for jumping somewhere in the code or using any return data type. Please just use it for normal control flow. Don't manipulate the control flow using exceptions.
And never throw exceptions in destructors. That's very important.
Highlight this in red.
Yeah.
Why shouldn't we throw an exception in a destructor?
When you're in a destructor, it might be that you are currently in an exception because an exception occurs and then your scope ends because the function is over or whatever. So the current program might be destroyed currently, and you cannot be in an exception calling another exception. So as soon as this happens, I think the program ends, it determines. So you should not throw exceptions in destructors.
Okay. Any final questions to exceptions?
Okay, I think in the interest of time, we will skip the cast and move it to next week. Then I think we earned also a good beverage with our practical stuff. And yeah, thanks for being here, and we will see each other next week.
Thanks
No,
for being here.
Not
and
next week, in 2 weeks.
in 2 weeks, but
We will
still
be-
all the best for
Yeah.
assignment 1. And yeah, let's see again in 2 weeks.
Thank you.
Thank you.